Ah, I see. Uh-oh. Hold on, I need to check something else really quick. Actually, I don't, because... Huh, okay, I guess... that's annoying. Okay, I'll have to check my last VOD. Okay, yeah, my microphone seems to have disconnected at some point. Probably because of a Windows update. So... Uh-oh. I may have not have had audio in the last stream. I didn't even realize. I didn't check. It may have just been like a no mic stream. Anyway. Oh well. Doesn't really matter. So yeah, we're doing set theory game today because, well, the weekends, normally I would do a Star Force stream, but Juka is going to be away for 3 weeks. So I figured, I might as well squeeze in another one of these. So yeah, if you're not familiar with set theory game, don't worry. It's another one of those lean math server games. I played Natural Number Game semi recently and got through pretty much the entirety of that. So we're just going to do the same thing this time with set theory game. So yeah, this one says, welcome to the set theory game, an introduction to mathematical proof. In this game, you will solve a sequence of levels by proving theorems. The game is based on an interactive theorem prover called Lean. The theorems in this game will be about sets. A set is a collection of objects. The objects in the collection are called elements of the set. For example, the set of planets in our solar system has 8 elements: Mercury, Venus, Earth, Mars, Jupiter, Saturn, Uranus, and Neptune. And Pluto does not count as a planet, sadly. We live in a post Pluto demotion world. Read this. Learning how to use an interactive theorem prover takes time. You'll get the most out of this game if you read the help text like this one. To start, click on Subset World. Or open Game Info in the context menu, I think is what those are called. On the top right for resources, links, and ways to interact with the Lean community. Okay, so I'm like still fresh coming off of my cold. I feel mostly better at this point. Like, I think the worst part is just the cough, like the occasional cough. I guess I am having a little bit of trouble breathing through my nose right now, but like, otherwise I'm mostly fine. I guess I am a little bit more tired than usual too, but eh. Alright, so welcome to Subset World. In this world, you will learn about sets and subsets, and you will also learn the basics of proving theorems in Lean. The elements of the sets in this world will come from a universe called U. To specify what an object belongs to, specify an object X belongs to the universe U, we write X colon U. Right. So it's like type notation. To specify that A is a set of objects from U, we write A colon set U. Okay, that's interesting. Huh. Oh, geez. Hello, fellow proof assistees. The entire last stream's voice audio is lost media. Yeah, that's unfortunate. Stupid Windows. I'm kind of mad about that one. This is one of the better ones on the Lean Game server. Oh, okay, cool. There are no impossible puzzles here, unlike Nat Num Game. So you'll have 100% completion satisfaction. Hooray! You know, actually, what's really funny is someone just yesterday posted the proof to Fermat's last theorem in the Alex Diener Discord. So, yeah, technically, I guess you could try to encode that in in lean and solve it that way, maybe. I don't know how doable that actually is. I'm not going to attempt it. Well, apparently someone recently uploaded a YouTube video that kind of explains it at length. I think they said it was like 9 hours long or something. I don't know. I feel like I'd get so lost before I ever before I ever got to a point where I felt like I could actually implement that in lean. Okay, so in parentheses, the terminology used in lean is that X has type U and A has type set U. Okay. So I guess this is trying to say that A is a type, sort of. But no. They're being very specific in saying that A has type set U. But I guess that's sort of how you would think about it. Like this is, I think this is their way of working around, like type in type, leading to a paradox. And so like I've seen like stratified type universes before, where you have like U1, U2, U3. It looks like they're doing something like U and set U here instead. So we'll see how this plays out. This is just my impression from my somewhat preconceived notions that I've gathered from other dependently typed languages. Ah, yeah, that's true. You might not have access to the required theorems in the game itself to do that, but you can always derive them from scratch if you need to. If you need those helpers, you could create them. Probably. I don't know. Actually, maybe not. Yeah, maybe not. There might be some constructs in the language that require like actual language support to use, and maybe they restrict those. So I don't know. Who's to say really? To say that X is an element of A, we write X element of A. You can enter the symbol element of by typing \mem or \in followed by a space. You'll prove theorems in this game by using tools called tactics. The aim is to prove the theorem by applying tactics in the right order. Let's learn some basic tactics. Click on Start below to get started. Okay. Read this first. Each level in this game involves proving a mathematical statement, the goal. When you give a proof of this statement that is accepted by lean, we say that you have closed the goal. Okay, in this first level, you're going to prove that if X belongs to the universe U, A is a set of objects from U, and X is an element of A, then X is an element of A. Uh-huh. Weird. I mean, if we already know this, then we can always derive this. We don't need the first two things, do we? I mean, like, okay, I mean, it's probably good to establish that anyway, but I feel like that's not necessary. You should see U. Uh-oh. How do you read that again? Is that U has type? Or no, or is that U belongs to type? I forget. How did they want me to read that? I want to go back. Okay, so supposed to say object X belongs to universe U. We write this. Specify that A is a set of objects from U. We write A set U. Okay, so they don't use like a specific like hard and fast terminology for the colon here because this is belongs to universe, and in this case it is a set of objects from. Okay. Just I don't know why I'm being that pedantic, but I feel like it. I feel like that kind of stuff kind of matters. Every game here is gonna have a tactic recap at the start, which is nice for you since it's been a little while since NNG. Yeah, that actually is nice because I don't really remember too much about how to do stuff in Lean. See, my head is gonna get confused because there's this, and then there's also this. There's the colon, and then there's this. What do you normally call this anyway in math? I usually call it element of. But then I also like to think of this as being like, this is an element of this. But I know that they aren't the same thing. Like even in type theories, like these two symbols are different things. I guess this is more like this thing has type whatever. So U has type, X has type U, and A is a set U. Interesting. So these are like different things entirely. Type and set. Fascinating. Under objects in the pane to the right. Oh, okay, so we have this. Okay, so they even explain it here. That's cool. X and A kind of needs type for the statement to make sense, since if X isn't of type U, it wouldn't make sense for it to be in a set of U. Okay. So this means that X is an element of A. To enter the symbol, right, you can type either \mem or \in. Interesting. Okay, so mem is for like member. So X member of A. Or you can say X in A for short. Very, very interesting. I feel like they don't talk about the colon, though. Do they? No. Okay, so that's not in the definitions here. Oh, and H. H has type X member of A? Under assumptions. Oh, right. There's two views normally, right? Oh, this one doesn't have the... Isn't there usually like a... Oh, wait, no, it's this button. Okay, there we go. Letter H here is called an identifier for the assumption X in A. Yeah, welcome back to Lean. It's been a little bit. You'll improve goals in Lean using tactics. The first tactic you're going to learn is called exact. I remember you, sort of. Is used to close the goal. You can close the goal by typing exact followed by a proof of the goal. In order to complete this proof, type exact H in the text box under the goal and click on execute or hit the return or enter key. Okay, so I guess we want to do exact H here because that just makes sense to me. Because we have an H, we want this. Yeah, we want an X member of A. Yeah, and we have one. Okay, so congratulations, you have completed your first verified proof. Although this theorem was trivial, it illustrates an important fact. Although we called H an identifier for the assumption X in A, it is also recognized by Lean as a proof of the statement X in A. anytime you see H colon P listed as an assumption where P is some statement, that means that Lean will recognize H as a proof of the statement P. Okay, sure. Remember that exact is a tactic. If you ever want information about the exact tactic, you can click on exact. Yeah. Note that although H was a proof of the goal, X and A, you could not have closed the goal by simply typing H in the text box. Throughout this game, every move you make must invoke a tactic. Right. Because in other languages, you might be able to just put H, but not in Lean. Now click on next to see a more interesting use of the exact tactic. Okay. If A and B are sets, then we say that A is a subset of B if every element of A is also an element of B. The notation A subset of B means that A is a subset of B. To enter the symbol subset, type \sub followed by a space. All right, so I guess we don't have to remember this stuff because it's going to tell us how to do that here. Yeah, so if I ever need to like remember how do I type this weird, funny looking symbol, I can come back to the definitions and it'll tell me exactly how to do that. Okay. If you have H1 is a subset B, then H1 is a proof that if something is an element of A, then it is also an element of B. Thus, if you also have H2 is an X element of A, then you can apply H1 to H2 to conclude that X is an element of B. Oh. Fascinating. So this is sort of like a function almost. So if I can prove that like X is an A, then I can like apply H1 to that proof. And that should let me get a proof of X being an element of B. Okay, yeah, and they even use the word apply here. To apply H1 to H2, you simply write H1 followed by H2 with a space between them. Ah, so this is like traditional like Haskell style function application. So thus H1, H2 is a proof of X is a subset of B. See if you can use this to complete this level. If you need a hint, click on show more help. Okay. Fascinating. So you don't even need to use like the apply tactic here. They just want you to write H1 and then H2. And then that didn't work. Why? Why? See if you can use this to complete this level. If you need a hint, click show more help. Unknown tactic. Are they trying to trick me? What? Did I get a new tactic? No. Do I have to exact? Yes. Right, they did say that you're not allowed to do that stuff without a tactic. Every line of the proof needs some kind of tactic, so I guess exact is required here for that. Interesting. It's syntactic sugar for a function, actually, really. A \sub B is basically syntactic sugar for \for all. For all x \in u. Okay, for all x in u, x in A implies x in B. Wow, okay. Yeah, it did feel like it was a function. I did not expect it to just be like syntactic sugar like that though, but yeah, I guess that makes sense. Huh. This example is a better illustration of how the exact tactic is usually used. Often exact is followed by an expression that combines assumptions to prove the goal. In later levels, we will see other ways in which assumptions can be combined to prove a goal. Note that in this proof, h1 could be thought of as a function that can be applied to a proof of any statement of form x in A to produce a proof of x in B. Many proofs in Lean behave like functions. Okay, cool. Makes sense. In this level, we have... Oh, come on, don't do that. In this level, we have assumptions. h1 is a subset, or is a is a subset of B. Okay, so this is a function. H2 is another function. B is a subset of C. And H3 is X is an element of A. Okay. As we saw in the last level, H1, H3 is a proof that X is an element of B. Uh-huh. Makes sense. Unfortunately, that is not the goal. So we can't use exact H1, H3 to close the goal. However, we can use the proof H1, H3 to justify adding an H4 to our list of assumptions. To do that, we'll use a new tactic, have. Okay, so we're bringing back have. Use have to assert a statement that you can prove from your current assumptions. You must give the new assertion an identifier. Be sure to use an identifier that is different from those already in use. If some expression T is a proof of a statement P, and H is an identifier that is not in use, then have H colon P. Okay, this is like the assignment, or I guess this is like the definition. T. We'll add H colon P to the list of assumptions. Okay. There are two variations on the have tactic. So I feel like have is like your way of like introducing a lemma. There are two variations on the have tactic. Sometimes you want to assert a statement P, but the proof of P is too difficult to be given in one line. In that situation, you can simply write have H colon P. Of course, you must still justify the assertion of P, so the proof of P becomes your immediate goal. Once the goal of proving P has been closed, you will be able to return to your original goal with H colon P added to the assumption list. If you write have H defined as T, Lean will try to infer the type of H. Okay. Yeah, that's basic type inference. Yeah, basically a variable declaration. That makes sense. To get started on this proof, type have H4. Oh, okay, so you want me to actually start typing these funny things. Have H4 colon X mem B defined as H1, H3. Okay. Mem. I don't know, I think that's just funny to say. In this text box, and click execute or hit return or enter call, you can enter symbol mem by typing mem or in. Okay. Notice that H4 colon X mem B has been added to the list of assumptions. Can you complete the proof now? Yes, I think. So I can probably do like an exact H2, H4, and then we're done. You can use the have tactic to add a new statement to your list of assumptions, as long as you can justify it with a proof. For further information, click on have in the list of tactics on the right. I think I've already done that. Yeah. Just like a normal programming language. Yippee! If P and Q are statements, then P implies Q means if P, then Q. To enter the symbol implies, type imp. It's short for implies. The most straightforward way to prove a statement of the form P implies Q is to assume that P is true, and then prove Q. To do that, we'll need a new tactic, intro. Okay. So use intro to introduce either a new assumption or a new object into your proof. This was how you made like a lambda, I think, right? Sounds kind of familiar. Since our goal in this level is the statement x member of A implies x member of C, our first step for this proof is to assume x is a member of A. To introduce that assumption, assigning it the identifier h3, type intro h3. Okay? Notice that h3 colon x mem A is now listed under assumptions, and your new goal is x mem C. You could also skip the have and just do it in one line. Oh, but the game wants me to use the have. I feel like, you know, it's better to interact with the game as intended. Like they want me to do it. Use intro to introduce either a new assumption or a new object into your proof. There are two situations in which you can use the intro tactic. If you're proving a statement of the form P implies Q, then you can use the tactic intro H to introduce the assumption H colon P and set Q as the goal. Be sure to use an identifier that is not already in use. If you are proving a statement of the form for all x, P of x, where P of x is some statement about x, then you can use the tactic intro x to introduce a new object x into the proof. Okay. Be sure to use a variable name that is not already in use. The goal will then be px. Okay, so these are very similar. Because I think the for all is sort of like a generalized form of this, of the function, if I remember correctly. Okay, so what are we trying to prove? Let x be an object from the universe U. And let A, B, and C be set such that A is a subset of B, X is a member of B, implies X is a member of C. Then X is a member of A, implies X is a member of C. Okay. So I've introduced H3. So H3 was, I guess, X mem A. And I can see it if I scroll down. Yeah. And then we have this guy, A subset of B. So we want to do like an H1, H, the new one. Was it H? Wait, H3. But I want to assign that to a new thing. So have H4. So that should be okay, right? I don't think I need to be specific with this, do I? Like, I think it can infer that. Then we go H2 on H4, and then we exact that, and then I think we're good. There we go. Okay, so yeah, they popped up some hints here. Just as you were able to apply h1 to h3 in the last step, you can now apply h2 to h4 to prove the goal. Does this change based on what number you use? What if I call it h5? It does change! That's crazy! Tricky Tony thought of everything. In general, if your goal has the form P implies Q, then the tactic intro H will add H:P to the list of assumptions and set Q to be the goal. If you have assumptions H1: P implies Q and H2 is a P, then H1, H2 is a proof of Q. Okay, yeah. Another example of proof acting like a function. Proof of P implies Q can be thought of as a function, which, when applied to a proof of P, produces a proof of Q. As usual, for more information about the new tactic intro, you can click on the intro tactic, as I have already done. And we got a new definition here. P implies Q means that if P, then Q. You can enter the symbol implies by typing imp. If your goal is P implies Q, the tactic intro H will introduce the new assumption H is a P into the proof. Oh, hold on. I gotta be right back. Okay, that was weird. There's something strange in my mouth. Don't know what that was. Okay, so what was I saying? Yeah, tactic intro H will introduce a new assumption H:P into the proof, set the goal to be Q. Should use an identifier H that's not already being used. If you have an assumption H:P implies Q, oh, what's this? If you also have HP:P, then HP. Oh, okay. Why do they call it HP like this? That's weird. I mean, I guess it kind of makes sense rather than like using a number. I mean, fair enough. This is just modus ponens. All right, we're good. Moving on. How do you prove that one set is a subset of another? To prove that A is a subset of B, you have to show that if some object X is an element of A, then it's also an element of B. To do that, you'll have to introduce an object called X into the proof. The object denoted by X could be anything, so we say that it is arbitrary. In this level, we start with a simple example of this kind of proof. We're going to show that if A is a set, then A is a subset of A. Okay, let me reread this. Okay, so the object denoted by X could be anything, so we say it is arbitrary. Oh, I see. Right. Let A be any set, then A is a subset of A. Huh. Okay. So our first step is to introduce an object X into the proof. To do this, we type intro X. Huh, okay. Is that something they mentioned? Not really. They don't talk about how this interacts with subset. But I guess subset is a function anyway. So intro X. Okay, yeah, we have already seen that the intro tech can be used to introduce a new assumption into a proof. This step illustrates the second use of intro, introducing a new object into a proof. Okay, so here we deconstruct the syntactic sugar for subset earlier. Notice that x:(u) has been added to the list of objects. Oh, yeah, they actually call them objects. Is that the same in the other view? Yes. And the goal has changed to x member of A implies x member of A. Fortunately, you already know how to prove a goal of this form. I do. So that would be intro, right? This situation should now remind you of your first proof in level 1. Okay. Interesting. So I had to do like a double intro. Interesting. The theorem you have proven in this level shows that the subset relation has a property called reflexivity. We have given the theorem the name subset.refl. You'll see it in the list of theorems on the right. Oh. Oh yeah, that is there. This theorem is included in Lean's mathematical library, mathlib. In mathlib, the name of the theorem is set.subset.refl. Okay. Many other set theoretic theorems in this game have set dot at the beginnings of their names in mathlib. Okay. So this is like a real thing in the real Lean. In editor mode, they call everything objects. But in the other view, they separate objects and assumptions. Oh, fascinating. But I guess objects and assumptions are basically the same thing. Which is why the editor view probably just lumps them all together. It's a for all statement in disguise, as mentioned before. I see. So it's it's a for all, and then inside of that for all is an implies, which is why we have to do 2 intros. Okay, I see. Okay, so subset.refl. If you have A is set U, then subset.refl A is proof that a proof of A is a subset of A. In mathlib, the name of this theorem is set.subset.refl. Okay, so I just basically need a set. So if I have a set, then I can prove that the set is a subset of itself. That is so interesting. To start a proof, you should look first at the goal. What needs to be done to prove the goal? In this level, the goal is A is a subset of C. What does that tell you about how to proceed? Proceed. That word is forever tainted in my mind. If you know, you know. Okay, now it's purple because we unlocked it from the last level. Why is this? Oh, interesting. These are like different categories. Okay, I see. So there's like the super categories, and then you have like the sub categories underneath them. Or I guess subsets. Sets? In the set theory game? No way. Okay. So what are we trying to do? Subset.trans. Suppose A is a subset of B, and B is a subset of C. Then A is a subset of C. Okay. So we have H1 is a subset, or A is a subset of B. We have B subset of C. Want A subset of C. And we probably need to do an intro, right? Uh, See, this is the hardest part, is figuring out what should I name? What should I name it? I mean, we already have an A, according to this. Oh, or is that implicitly using the letter A? So if I write intro A, oh, okay, so that was implicit. Okay. So I guess I could actually just leave this off and it would just call it A, but I feel like that's bad form. Okay. I don't feel like this is particularly hard, but this is the first world. So we just need to do another intro, yeah? Intro H. I mean, we have an H1 and an H2. Let's call this one H3. Does your situation now remind you of a previous level? So now I can like have H4, which will be like H1 applied to H3. Wait, no, I need to use the equal. And now we have H4. And now we can just do it again. Oh, wait, no, this should be H2, H4. And then we should exact H5. There we go, cool. Level completed. The theorem you have proven in this level shows that the subset relation has a property called transitivity. We have given the theorem the name subset.trans. All right, and there we go. That subset world done. We did it. Yay! A is actually the default name. Yeah. That's so weird. I feel like I would never want to do that. It just feels wrong. Like, you should always give stuff a name if you can. Don't let them just pick names for you. If A, okay, so where are we? We're in the complement world. If A is a set of objects from the universe U, then the complement of A, denoted A to the power of C, at least that's how I'm reading it, is a set of all objects in the universe U that are not elements of A. I'm guessing this doesn't stand for power of. Didn't we already do like a power world or something previously? So this wouldn't be that, right? This is just a. I guess I should call this a complement. I don't know why they'd use this superscript notation. It feels very like, power coded, but. So the complement of A is known as AC, A complement. The set of all objects in the universe U that are not elements of A. For example, if U consists of all people, and A is the set of people who are more than 6 feet tall, as in not me, then A complement is a set of all people who are at most 6 feet tall. That includes me. I'm here. I'm in A complement. In this world, we'll see how to prove theorems about complements. To work with complements, we'll need to understand negative statements. That is, statements that say that something is not the case. If P is a statement, then not P means it is not the case that P. To enter the symbol not, type not. A common method of proving a negative statement is proof by contradiction. To prove a statement of the form not P, you can assume that P is true, and then show that this assumption leads to a contradiction. The tactic to use for this kind of proof is by contra. This is a message. You must go out to your local video game store and buy a copy of Contra. Oh wait, they're getting rid of physical games. Too bad. For the theorem in this level, your goal is not A is a subset of B. Wait, how does that work? my brain hurt. Is not A the complement of A? To use proof by contradiction in this proof, you must begin by introducing the assumption H3. A subset of B. To that type, by contra H3. Oh, so we're not going to use intro? Implicit parens? Huh? Oh, are we talking about these things? The implicit arguments? I feel like that's what these are, right? These are implicit arguments. Because that's the same notation that they use in Idris. Suppose X is an element of A, and X is not an element of B. Then not A is a subset of B. It's not. Oh, A subset B. Oh, okay, I see. So there should be parentheses around like here. Okay, that makes more sense. So if X is in A and not in B, then it is not the case that A is a subset of B. Because there's an element outside of B that is in A. And we can prove this by contradiction, apparently. But we're introducing an assumption, right? So, like, couldn't we have used intro instead? I feel like intro would be basically the same thing, wouldn't it? The not is applying on the whole statement, not just A. Yeah, okay. Notice that the goal is now false. Is it? It is. Okay, what? Okay, I'm curious. Bro. What? They're the same thing. They're the same damn thing. Okay, sure. I guess if you want to have multiple constructs in your language that mean the exact same thing, sure. To achieve that goal, you must prove contradictory statements. You can do that by using have to assert X member B, which will contradict H2, X not a member of B. Wait, hold on. So they want to use have. To assert that X is a member of B. How do you mean? Okay, we also have stuff to read. Let's do our reading. Not P means it is not the case that P. To enter the symbol not, type \not. If your goal is not P, you may be able to use the push neg tactic, push neg, to re-express the goal as an equivalent positive statement. Is this like contra-positive? If not, then a good strategy is to use proof by contradiction. The tactic by contra H will introduce the assumption H. H is a P. Oh, okay. I think I'm starting to get it. So like if your goal is like a not, then proof by contradiction is usually the way to go. Set the goal to be false. Aha. If you have an assumption H colon not P, you may be able to use a tactic push neg at H. Push neg. Push neg. Interesting. To re-express this assumption as an equivalent positive statement, Lean treats not P as meaning P implies false. Okay. So if you also have HP colon P, then HP will be a proof of false. Okay. That means that by doing a proof by contradiction, oh, sorry. That means that if you are doing a proof by contradiction, so your goal is false, then exact HP will close the goal. Okay, could I have done that here? Okay, well, my goal is currently sorry. By contra. If your goal is not P for some statement P, then the tactic by contra H will introduce the new assumption H colon P and set the goal to be false. If your goal is a statement P that is not a negative statement, then by contra H will introduce the new assumption H colon not P. To achieve your new goal, you will need to establish H1 colon Q and H2 colon not Q for some statement Q. If you can do that, then H2, H1 will prove the goal false. Notice that H1, H2 will not be recognized as a proof of false. The negative statement must come first. Oh yeah, because you have to apply it like a function. How interesting. Okay. So I guess I need to take U and do something with U. Because I think I can extract a proof of false by using this guy, right? Because this is just X mem B implies false. So I would need... Wait, no, but then I need to assert that X is a member of B. And how would I do that? Oh, by using H3, of course. Because A is a subset of B, according to H3. Okay. And H1 says that X is a member of A. So if X is a member of A, then I should be able to apply H3 to H1. And that should give me something, right? Oops, I need to do equals. Okay, we got a new hint. You can think of H2 colon X not a member of B, which is shorthand for H2 colon not X a member of B, as meaning if X is a member of B were true, then that would lead to a contradiction. In other words, X is a member of B implies false. Applying this to your new assumption H4 is X member of B will give you the contradiction you need. In other words, exact H2, H4 will close the goal. Okay. I didn't really need that hint, but sure. I get it. I get it. By contra can also go the other way, proving P by assuming not P, which does assume the law of excluded middle. as opposed to intro. Oh. Really now? My contra can go the other way. Oh yeah, I guess that is true. If your goal is a statement P that is not a negative statement, then by contra H will introduce a new assumption H, colon, not P. Huh. Weird. So does that mean that lean assumes the law of excluded middle in general? I feel like that's different from most proof assistants, because usually most proof assistants are based on constructive logics. They don't have law of excluded middle by like default. Huh. That is a very important distinction. Okay, what do you have to say? Why are you yapping to me? Level complete. You can use the by contra tactic in any proof to assume the opposite of your goal. But it is most useful when the goal starts with a symbol not. After using the by contra tactic, your goal will be false. To complete a proof by contradiction, you must prove contradictory statements. If your goal is false, and you have assumptions h1 colon p and h2 colon not p for some statement p, then exact h2, h1 will close the goal. Note that exact h1, h2 won't work. You must list the negative statement first to establish a contradiction. Okay. You have the option to assume it, which is what by contra does. You assume. Get it? Because it's an assumption. Okay. If you have A is a set U, then A complement is defined. Stop that. Is defined to be the set of all objects in the universe U that are not elements of A. That means that if you also have X colon U, then the statements X member of A complement and X not a member of A are equivalent. True, I guess so. We express this by saying that the statement X member of A complement, oh no, is if and only if X not a member of A is true. I'm sorry, I remember seeing this symbol a lot in my university days, and it's kind of given me that PTSD, you know, from your math classes. The symbol means if and only if, and you can enter it by typing \IFF, of course. You can enter the superscript C in the notation for the complement of a set by typing \compl or \C. In this level, we're going to prove that the statement X is a member of A complement if and only if X is not an element of A is true. And to do it, we'll use a new tactic, ruffle. We're introducing the ruffles. Wowie zowie. I'm surprised that it took this long to get there. The ruffle tactic can prove any statement of the form P if and only if Q, if P and Q are statements that are equivalent by virtue of the definitions of the symbols occurring in them. Okay, that's interesting. This if and only if sounds like it's probably syntactic sugar for something. Because, like, weren't we using ruffle before? But we didn't have this guy. I swear we used ruffle before. Am I wrong? I thought there was a ruffle before. If P and Q are statements by that are equivalent by virtue of the definitions of symbols occurring in them, we say in this case that P and Q are definitionally equivalent. The ruffle tactic can also prove statements in the form X equals Y. Yeah. If X and Y are definitionally equal, that is by virtue of definitions. Whoa. So is the equals just like syntactic sugar for this guy? Kinda? So this feels like this kind of feels like isomorphism is being treated the same as like equality, if I'm not mistaken. Like they're applying like isomorphic reasoning here. Interesting. So either equals a sugar for if and only if, or it's the other way around. Huh. But can I do this? No, I can't do that. I have to do this. I have to do that. Oh, they're haters. They don't like your notation. You do this? No. The proof of this theorem in this level is very easy, since X is a member of A complement and X is not a member of A are definitionally equivalent. So ruffle will close the goal. Is that so? Okay, so let's look at this guy. P if and only if Q means P if and only if Q. If you can enter the symbol if and only if by typing IFF, if your goal is P if and only if Q, if P and Q are definitionally equivalent, then ruffle will close the goal. If you have H1 is a P implies Q, and H2 is a Q implies P, then if and only if dot intro H1 H2 is a proof of P if and only if Q. I mean, that makes sense mathematically. I'm trying to... Okay, so this is a different intro, I think. Because they namespaced it as if dot intro. So exact if dot intro H1 H2 will close the goal. Oh, so this is not a tactic. So you need exact still. If you don't yet have proofs of P implies Q and Q implies P, then apply if dot intro will set P implies Q and Q implies P as your goals. In this situation, the tactic constructor has the same effect as apply if dot intro. Constructor. Okay, I've not seen that one yet. If you have an assumption H colon P if and only if Q, Lean will recognize H dot MP as a proof of P implies Q, and H dot MPR as a proof of Q implies P. Okay, so this is weird. It's almost like H is a pair of proofs. Like these are the projections. MP and MPR. So like if you had like a tuple and you went like index 0 and index 1 of the tuple. You may also find it helpful to use H in the rewrite tactic. That is fascinating. Because I wouldn't think of something like this, like something that's tuple-ish like this as being the same as equality. Okay, we also have C. Let's go look at C. C. If A is A of all... What? If A is of objects from the universe U, then AC, A complement, is a complement of A. As A complement is a set of objects from U that are not elements of A. You can enter the symbol C by typing \compl or \C. MP is for modus ponens. Ah. The statements are just syntactic sugar for tuples. Statements are just syntactic sugar for tuples? Okay, that's wild. Whoa. My brain hurt. Or unless you mean like and statements. Like anding stuff together. Like this and that. In which case that makes sense. Riffle. If your goal is the statement of the form P if and only if Q, and P and Q are definitionally equivalent, that is, equivalent by virtue of the definitions of the symbols occurring in them, then the riffle tactic will close the goal. It will also close a goal of the form x equals y if x and y are definitionally equal. Yeah, that's crazy. So here the goal is to just riffle, because A is an element of A complement. Apparently is just definitionally equivalent to this. The name of the tactic riffle is short for reflexivity, which is the property of both equals and if and only if. That is the basis for the tactic. Okay. Fascinating. We have given the theorem proven in this level the name mem compl if and only if. In the next level, we will see how we can use it to prove theorems about complements. Okay. In the last level, you prove the theorem mem compl if you have A is set U and X in U, then mem compl if AX is a proof of the statement X is a member of A complement if and only if X is non-element of A. Okay, you want me to keep reading? Got it. You could think of the statement X is a member of A complement if and only if X is not a member of A as saying that if X as an element of A complement occurs anywhere in a proof, you can replace it with X is not a member of A. There's a tactic called rewrite that can be used to perform such replacements. Okay, so now we're bringing in the rewrites. You get to try out the rewrite tactic in this level. Oh. Okay, now things are getting crazy. As usual, to prove a subset statement, you need to introduce both a new object, X, and a new assumption, H2. You can do it in one step with intro X, H2. Okay. All right. Actually, hold on. There's more reading. Okay, so we got this one. So if you have A set U and X is U, then mem compl if AX is a proof of the statement Yeah, X member of A complement if and only if X is non-member of A. In MATLAB, the name of this theorem is set.memcompleIf. Okay, so that's another thing that's part of the lean mathlib. Rewrite. If the expression T is a proof of a statement of the form P if and only if Q, then the tactic rewrite, okay, yeah, the square brackets T will replace P anywhere that it occurs in the goal with Q. I see. If you want to replace Q with P, use rewrite. Right. And we want, so this is the funny arrow. So \L is to do the arrow to reverse. To do the replacement in an assumption H, use rewrite at H. Right. The rewrite tactic can also be used with equations. If T is a proof of an equation, P equals Q, then rewrite square brackets T will replace P with Q wherever it appears, and rewrite, I guess, yeah, \LT will replace Q with P. To do multiple replacements, one after another, put a list of proofs inside the brackets like this. Rewrite T1, T2. Okay, now memcomple if AX is a proof of statement X is a member of A complement, if and only if X is non-member or non-member of A, which tells us that we can re-express the goal X member of A complement as X non-element of A. To this re-expression, use the tactic rewrite memcomple if AX. The rewrite tactic is smart enough to figure out some things on its own. If you had just written rewrite memcomple if, then Lean would have figured out how to apply the theorem memcomple if to get an equivalence that could be used to make a replacement in the goal. In other words, it would have figured out that the theorem memcomple if had to be applied to A and X. Okay, so I didn't need to supply these, is what you're saying. Similarly, you can rewrite memcomple if at H2 to rewrite out the meaning of H2. Lean will figure out that in this case, memcomple if has to be applied to B and X. Okay, so hold on. What did we have at this point? This is our goal. And wait, why did we do? Oh, let me look at this one at a time. Ah, right, because this is 2 layers. Right. And then we do the rewrite on AX. What does that do? It changes our goal. I see. Right, and rewrite always targets the goal by default, unless you use at. So now you're telling me to use a rewrite here on H2. I could do BX at H2 if I want to be specific. Okay, I see. And then what? So now we have not. So A is not a member, or X is not a member of A, and we have H2, which is X not a member of B. And we have this H1. A is a subset of B. So I feel like this is the point where I need to use like by contra probably. Because this is a negation, right? The goal is a negation. Oops, not you. By contra should be helpful for that, right? I'm going to go with that, I think. By contra. H3. Okay, so now I have H1 and H3. So I could do like a have H4, H1 applied to H3. And that gives me an X element of B, but I also have X not element of B. Let me get a little bit more water before I continue here. Okay. So I should be able to turn my H2 into... Actually, no, I don't need to do that because it's already a function, right? So wouldn't I be able to do like exact... Go back. You're the function, so H2 needs to be applied to H4. Okay, cool, there we go. The rewrite tactic is often useful for writing out definitions. For more information about how it works, click on rewrite in the list of tactics on the right. You can also use RW instead of rewrite. There's actually a small difference between RW and rewrite, but the difference won't concern us in this game. Really? There's a difference. You'll find the theorem you proved in this level listed as compl subset compl of subset. This will be useful in the last level. Okay, so remember this guy. This guy is very important. If you have H is a subset of B, then compl subset compl of subset H is a proof that the complement of B is a subset of the complement of C. Oh, interesting. I guess that makes sense, like thinking about it logically. Because like if you were to imagine like two bubbles, like like if there's like a set A, and then there's a bigger bubble set B that surrounds A, then everything that isn't in B, so like all the space around the outside of B, would be smaller than the number of elements that are not in A, because that would include the stuff in B. So the name of this theorem is set compl underscore subset compl of subset. And I think, yeah, nothing else to look at here. How do we prove that two sets A and B are equal? One way to do it is to use the theorem subset.antisim. This theorem is predefined in this game. You don't need to prove it. If you have h1 colon a subset of b, then h2 colon b subset of a, then subset.antisim h1 h2 is a proof of a equals b. The theorem subset.antisim says that the subset relation has a property called antisymmetry. Okay. Interesting. So now we get equalities. But what if you don't already know that A is a subset of B and that B is a subset of A? In that case, you can use a new tactic, apply. If your goal is A equals B, and you write apply subset.antisim, then Lean will figure out that the theorem subset.antisim could be applied to prove the goal. If only you had proofs of A subset of B and B subset of A, so we'll set these two statements as goals. My brain is melting. In that case, you use the new tactic, apply. Your goal is A equals B. You apply subset.antisim. Okay, so that creates two goals. So you're telling me I should start with this, right? Because we have an equality here. If your goal says that two sets are equal, a good way to begin is with apply subset.antisim. Later we'll see a second approach to proving sets are equal. Okay. Also, this level introduces push neg. Okay. I'll look up push neg in a second. Okay, so you need to prove that A is a subset of ACC, and ACC is a subset of A. Makes sense. In this level, your goal is ACC equals A. That's a complement of A complement is equivalent to A. So, yeah, that's a good way to start. You've seen this before in NNG. Apply can work in reverse, where you have substatement P implies Q, and your goal is Q. So applying P implies Q will set the goal to P. Since you can prove Q by having the P. Okay. Yeah, I remember vaguely, but like, I don't know. It's been a little bit. It's been a little bit. Okay, your immediate goal now is to prove that A complement is a subset of A. Once you close that goal, you'll be asked to prove the second goal, A is a subset of A complement. Oh boy. So we have tactics. Oh, you can use the apply tactic to work backwards from the goal. Suppose you think that you will be able to use some theorem T to prove the goal. In other words, you think there is a proof of the goal of the form T applied to something, where the question mark needs to be replaced with a proof of some statement P to which the theorem T must be applied. The tactic apply T will then set P as your goal. If T must be applied to more than one proof to establish the goal, then apply T will set all of the needed proofs as goals. Push neg. If your goal is a negative statement, then the tactic push neg will try to re-express it as an equivalent positive statement. Similarly, if an assumption H is a negative statement, then push neg at H will try to re-express H. Here's some examples of re-expressions performed by push neg. Not P is converted to P. Interesting. So I think this requires law of excluded middle, right? I'm trying to remember. Oh, this is De Morgan's law. Not P or Q is converted to not P and not Q. Uh-huh. Not P and Q is converted to P implies not Q. Not P implies Q is converted to P and not Q. Not for all x, Px is converted to there exists x such that not Px. And there, I guess there does not exist x such that Px is converted to for all x, not Px. Okay. Think I kind of understand. Sort of. Oh boy. So right, my goal is to do this. No, my immediate goal is this one. And apparently at some point we're going to use push neg. Whatever that means. Well, it does say not P would be converted to P. This looks kind of like a not. I think we might need to rewrite. Because... where was it? Because we had this, right? So we can convert a complement into x not a member of A. So I think we want to do that. I mean, we also have this guy. I don't know if we want to use this one, though. Actually, I don't know if we can use this one. So if you have A is a subset of B, which I don't, I think I have this. This is the situation I'm in right now. So I think we want to rewrite. How do we want to rewrite this, though? I want to take the thing on the left and turn it into a thing on the right, don't I? I can't do that right away because I don't have an X. So I need to intro. Okay, that's starting to look closer to what I want. We have another arrow. I guess I should probably do H. Okay, yeah, now they're giving me more hints. Write out the definition of complement in H. Quantified De Morgan. Interesting. Write out the definition of complement in H? You mean like rewrite it? Because I feel like that's what you want, right? You're asking me to do like this mem compl if at H. Okay, yeah. That seems good. The assumption H now says A is not an element of a complement, which means not A is an element of, or what? Parentheses, right? So it means A is not the case that A is an element of a complement. It will be helpful to write out the definition of complement again in this assumption. Okay. What if I do this then? Oh. Now H says, yeah, A is, well, it is not the case that A is not a member of A, which means not A is an element of A. Of course, this can be simplified to just A is an element of A. And this is where we use push neg. To simplify the assumption, write push neg at H. Aha. Exact H. And the proof of the second goal is similar. Okay. Cool. We're doing it. We're making it happen. So I just gotta do this. Can I do this twice? No. Wait, wasn't there like a repeat? I swear that was like a repeatedly just do the thing again. Wait, is this wrong? Okay, hold on. Maybe I'm doing this wrong. I need to hold my horses. Why is this? Why does that not work? There are two ways to complete this proof now. Since your goal is a negative statement, one natural strategy would be to use the proof by contradiction. Oh, is it because... Wait. Oh, I need to rewrite the goal. Oh. That's why. What was my goal before? Hold on. Oh yeah, I guess that makes sense. I was supposed to rewrite out the goal. No, that makes sense. You're leaning. We're learning minus the R. Wrong target. Junat. Who's Junat? Alter ego? Dark Johnat? There are two ways to complete the proof now. Since your goal is a negative statement, one natural strategy to use would be proof by contradiction. A second possibility is to imitate the approach in the first half. Write out the meaning of complement again in the goal, and then use push neg to simplify the resulting double negative of goal. Either approach will work. Okay, cool. I'm just going to do it again. Yeah. I don't even have to do it at H, because that's cool. Okay. Interesting, interesting. The push neg tactic can re-express a number of different kinds of negative statements as equivalent positive statements. Use push neg to re-express a negative goal, and push neg at H to re-express a negative assumption H. We'll see many more uses of the apply tactic in this game. For more details about the use of these tactics, click on push neg or apply under the list of tactics. Yeah, I've already done that. We have given this theorem the name compel. Both this theorem and the one in the previous level will be useful in the next level. Okay, so I need to use both this one and the previous one. So we want compel subset compel of subset, and we want compel. All right, so what's the final boss of this world? In this last level of complement world, you'll prove a statement of the form P if and only if Q. The most useful theorem for this purpose is if and only if dot intro. Okay. If you have H is proof of P implies Q, and H2 is proof of Q implies P, then if and only if dot intro, H1, H2 is a proof of P if and only if Q. Yes, I know that. As we saw in the last level, that means you can start your proof with apply if and only if dot intro. Okay. I will do that. Lean will set P implies Q and Q implies P as goals are needed to complete the proof. My evil twin, who really loves the 6th month of the year. For the proof in this level, apply if and only if dot intro will create the goals. A subset of B implies B complement is a subset of A complement, and B complement is a subset of A complement implies A subset of B. Okay, so we have goals. We have many goals. We have too many goals. Okay, so what did we learn? We learned compel. If A is a set, then the complement of A is proof of ACC equals A. So we're going to use this for rewriting, clearly, because it has equality in it. Which means we need to break this down to a point where we can actually start rewriting stuff. And they also said this one is useful. So B complement is a subset of A complement. Oh, no, so we need this assumption. If we have H1, if we have proof that A is a complement, if A is a subset of B, then the complement of B is a subset of the complement of A. We also got if intro, but I think we've already used it for what we need it for. Oh, constructor. If your goal has the form P if and only if Q, the tactic constructor will replace this goal with the two goals P implies Q and Q implies P. Okay, so this is equivalent. If your goal has the form P and Q, then constructor will replace this goal with the two goals P and Q. Oh. There are other situations in which the constructor tactic can be used, but these two are the ones that are most relevant for the set theory game. Fascinating. Should I get used to using constructor instead then? Instead of apply if dot intro? I don't know if it really matters. All right, so this is what our goal looks like. I guess I should intro, huh? Because like, what else am I gonna do with this? Well, I can. Oh, I could. I could apply, right? I could apply on the goal. But no, I need something to apply. No, I think we just intro. Sure, intro A. Fortunately, the theorem compl subset compl of subset can now be used to prove the goal. So this was the one that says that if we have A subset of B, then, yeah, no, that's exactly this. Dang. Second goal similar, but a little trickier. All right. Intro A. Let's see. But we haven't used the other tactic yet. Or sorry, the other theorem. We haven't done compl. So it has to be involved here, right? So this thing doesn't prove the goal, but it comes close. Do you see what assertion it will justify? Right, because these guys are backwards. What assertion it will justify? Oh. So if we use it, can I use this guy on this guy instead? And then get something crazy looking? But no, you're the wrong form, right? But you're a subset. Oh, I guess I don't want to try exact. I want to have. There we go. Fortunately, we can use the theorem compl to prove A complement equals A and B complement equals B. Aha. And those things should get us from H to the goal. We have seen in previous levels that the rewrite tactic can be applied to a proof of the statement of the form P if and only if Q to replace P with Q. The tactic can also be applied to equations. Yes, I know. So we want to do a rewrite here of compl at H. And then we want to do it again. And there we go. Now we can do exact H and we're good. Level complete. Yay! World clear. The proof in this level illustrates how previously proven theorems can be used in proofs. There's another tactic you can use if your goal has form P if and only if Q. In this situation, the tactic constructor will have the same effect as apply if and only if intro. That is, it will set P implies Q and Q implies P as goals to be proven. Okie dokie. Cool. Okay, I think I have time for one more world. Maybe. We'll see. Intersection world. There's gonna be intersections. There's gonna be cars. They're gonna like run into each other and crash. If A and B are sets, then the intersection of A and B, denoted A intersect B, is the set of elements that the two sets have in common. In other words, for an object to be an element of A intersect B, it must be an element of both A and B. For example, if A is the set of all round things and B is the set of all red things, then A intersect B is the set of all round red things. In this world, you'll prove some basic properties of intersections of sets. Okay? Talking about them red round things. When are we getting roundabout world? Speaking of roundabout, I've been reading the latest JoJo chapter for the JoJo lands. And oh boy, did Araki cook. I don't know. I don't want to get into too many spoilers for JoJo lands, but if you're a fan of the JoJos and you haven't read the manga, it's peak. You should definitely check it out. To work with intersections, we'll need to understand the word and. Okay. This is such a funny statement. I don't know. It just sounds so funny. You need to understand the word and. What even is an and? If P and Q are statements, then P and Q means P and Q. To enter the symbol and, type \and. For the statement P and Q to be true, P and Q must both be true. If you have H colon P and Q, that is H is a proof of the statement P and Q, then in lean, H dot left is a proof of P and H dot right is a proof of Q. That should be all you need to know to solve this level. Did we do this before? I feel like the left and rights were tactics at one point, but not. I feel like we've seen left and right, but not in the context of like this. But I swear we've seen the ands before. You have not Joed the Joe, as it were, not the anime nor any other media. Fair enough. Okay, yeah, P and Q means P and Q. If your goal is P and Q, okay, if you have HP, so P and HQ is Q, you can use and.intro HQ to get a proof of P and Q. So exact and.intro HQ will close the goal. If you don't have proofs of P and Q, then apply and.intro will set P and Q as separate goals. In this situation, the tactic constructor has the same effect as apply and.intro. If you have an assumption of this form, then you can use H dot left and H dot right. Yeah, didn't we decompose and ors before? I remember we did ors. Because I'm pretty sure that was where we did like the left and right stuff. Maybe we didn't do and. Okay, so I just need the left side of this H. So I guess we can just do H dot left. But I need to exact it, right? Level complete. Now we're ready to start proving theorems about intersections. Beep beep, honk honk. Oh, that was weird. In this level, we'll need to use the definition of intersection. The theorem that expresses that definition is called mem inter if. If you have x in U, or sorry, no, x is proof of U, A is proof of set U, and B is a proof of set U, then mem inter if xab is a proof of the statement x is an element of A intersects B if and only if x is an element of A and x is an element of B. Are we proving that? Or is that something that you just gave me? No, that's something you just gave me. If you have... Okay, yeah, that's basically the same thing that you just said. And here's intersect. Inter. Okay. So what does that have to do with and? I guess this is where it has the and. So you can like rewrite them this way. Yeah, I don't think we did ands in NNG. I think we did the ors. This looks unfamiliar. As we saw in the complement world, that means that the tactic rewrite mem inter if xab can be used to replace x is an element of A intersect B in the goal with x is an element of A and x is an element of B. Usually Lean can figure out x, A, and B on its own. So you can just write rewrite mem inter if, and you can use rewrite mem inter if at h to do the replacement in the assumption h rather than the goal. Okay. Rewrite mem inter if at h. Cool. Like mem compl if, mem inter if can be proven by using the ruffle tactic, but we won't ask you to prove it. It is predefined in this game. To enter the symbol intersect, you can type \inter or \cap. Why is it cap? Is it because this symbol is a cap? Because it looks like a cap, sort of? Like a cap that you put on your head? To start on this proof, try writing out the meaning of intersection in H. Okay. Okay, so yeah, that's what I just did. Now your situation is similar to the previous level. I see. Oh, we have to exact. I always forget this. There we go. Okay, easy. You should be able to combine ideas from the previous levels to solve this one. Okay, here we go. So now we're getting a little more serious, are we? Okay, so I want to rewrite the goal. I want to use mem inter if. Did we learn anything new? I don't think we got anything new this time, did we? Because I thought I'd have more theorems, because I just proved a thing, but I don't think it ended up in my list of stuff. Or maybe it's somewhere else. Although I would expect it to be here, if anything. Why can't I do that? Wait. Yeah, there's a... Oh, no. It has to be X is an element of A intersect B. Okay, I see. Oh. So that doesn't work. In that case, should I intro... Okay, now we have one of those. I'm wondering if I should intro again, though. Before I continue on my quest. Okay, well, what would this net me? Not much. I think we're gonna do another intro. So now I can do rewrite mem enter if h. Yes. Oh, and now that's my goal. Okay, cool. Oops, I keep doing this. You probably use a step like rewrite mem enter if at h in this proof. That step is actually optional. That was just bonus. Writing out the definition of intersection probably helps you understand how to proceed with the proof, but Lean doesn't need to be told to write out the definition. Oh, good for Lean, man. God. It will do that on its own. In other words, if you have h is an element of a intersect b, Lean will just accept h dot left as a proof of x is an element of a. Really interesting. In this level, we'll prove a statement of the form P and Q. To do this, we'll need another theorem, and.intro. If you have H1 is a proof of P, and H2 is Q, then and.intro H1, H2 is a proof of P and Q. Writing out the meaning of intersection in the goal will help you see what to do to complete this level. Okay. Right, and we just got and.intro. Okay. Doesn't seem too interesting. We haven't really unlocked much new. Oh, these are called examples. No wonder. I was like, why are we not getting new, like, stuff? But yeah, these are just called example. So we're in, like, the baby steps. Okay, so write out the meaning of intersection in the goal to help you see what to do to complete the level. So that means you want me to do a rewrite mem enter if. Now you can use an intro to prove the goal. I sure can. Once again, the use of rewrite was not really necessary. You can prove this theorem with a single step exact and.intro h1, h2. I could have, and I would have, but you told me not to. You were like, write out the meaning. So I was like, all right, fine. I'll play along. It's like when you finish a chapter and you're at the practice problems. Yeah. Of course, you know by now how to start a proof that one set is a subset of another. All right, I get you. I know what you're saying. You're telling me to intro A and then probably intro H as well, right? Because it's going to be an implication. Yep, okay. I get it. Writing out the definition of intersection in the goal will help. John Lean, why are you backseating so much? I know what I'm doing. Okay, this part is kind of more tricky, I guess. If you had HB, it's proof of A is an element of B, and HC is a proof of A is an element of C. Then and.intro HB HC would prove the goal. So there are two ways to proceed. One possibility is to use have to introduce the assumptions A is a member of B and A is a member of C. That is, if you can see how to justify those statements, then you can use and.intro to prove the goal. The second possibility is to use the apply tactic. Recall that if you write apply and.intro, then Lean will figure out that the theorem and.intro could be applied to prove the goal. If only you had proofs of A is a member of B and A is a member of C, so I'll set those two goals as statements. Or so those two statements as goals to be proven one after the other. Okay, fine. I would never back the seat. Couldn't be me. Alright, so apply and dot intro. Your immediate goal now is to prove that A is a member of B. Once you close that goal, you'll be asked to prove the second goal, A is a member of C. Okay. I'm guessing I would have gone to like a different dialogue branch if I went with the have route. If I took the have route. So if you want to see all the different dialogue in this game, you have to try doing the proof both ways, guys. This is how it is. Ugh. So what do? I need to prove A is an element of B. And I have, what, H1 to do that with. Sure, I guess I could do that. Do I have a rewrite for that? I feel like I should have something for that. Okay, not this. Not this. Not this. I mean, there's no... Wait, this is a function. You're a function. Okay, there we go. And then I can exact H2H. There we go. Cool, cool, cool. In general, if you think that some theorem T could be used to prove the goal, the tactic apply T will work backwards from the goal, setting as new goals any hypotheses that are needed for the application of that theorem T. If your goal has the form P and Q, then the constructor tactic will have the same effect as apply and .intro. That is, it will set P and Q as goals to be proven. Okie dokie. Who would a CYOA in my lean game? In the next level, we're going to prove that intersection is commutative. Uh-oh. That is A intersect B equals B intersect A. As a warm-up, in this level, we prove A intersect B is a subset of B intersect A. Okay, sounds good. Now I get a hint button, suddenly. They're gonna make me write out the definition, right? I think that would be smart. Let's do that. Because they've been telling me to do this, like, repeatedly. So it almost makes me feel like that's just good practice. Like, just do it because it'll help you. Right? Like, that seems good so far. So now I should be able to like end intro, right? And then I can use h right, or yeah, h dot right and then h dot left. There we go. We have given this theorem the name intersubset swap. Thus, from now on, any sets A and B, for any sets A and B, intersubset swap AB is a proof of A intersect B is a subset of B intersects A. Interesting. They're not just equivalent. I guess that's true. Or are we going to prove that here? Yeah, we're going to prove that here. As we saw in complement world, a good first step when your goal is an equation between sets is apply subset.antisim. Okay, apply subset antisim if you have an equation between two sets. I see. So if they aren't sets that we're talking about, then you might not want to do that. Makes sense. I mean, we are in the set theory game, so it kind of makes sense. For the theorem in this level, that will leave you with two goals. A intersect B is a subset of B intersect A, and B intersect A is a subset of A intersect B. Fortunately, you can prove both of these goals by using the theorem intersubset swap from the last level, which is this one. So if A is a subset of B, if A intersect B is a subset of, no, there's no if. A intersect B is a subset of B intersect A. Yes. And they said what to do here is apply subset dot antisim. So we'll start with that. And then we can just trivially use this, I guess. I mean, that seems pretty cut and dried, right? No? Am I misreading? Oh, I need to give it A and B. No? Do I have to apply? Okay, and I think that got rid of one of the goals. Now we have B intersect A is a subset of A intersect B. Oh, I see. Whoa. Oh, and I guess it just fills it in. Wait, do I ever need to? Oh. Ow. We'll prove one more property of intersections in the next level. Okay. Intersection is associative. Our goal in this level is again an equation between sets. In previous proofs of this kind, we started with the tactic apply subset.antisim, and that would work here as well. But we are going to try out an alternative, the tactic X. This tactic applies the principle of extensionality for sets, which says that if two sets have exactly the same elements, then they are equal. x. If your goal is a equals b, where a and b are sets, then the tactic x will introduce a new arbitrary object x into the proof and set the goal to be x is a member of A if and only if x is a member of B. Oh. Oh, you mean exact actually did work? Okay. Man. Okay, so what am I doing here? So they want me to use this X thing. I mean, I guess I can do that. They said start with X. Notice that Lean has written the goal as A intersect B intersect C equals A intersect B intersect C with no parentheses on the left. When an intersection of more than two sets is written without parentheses, Lean groups the intersections to the left. Oh, so it's left associative. So yeah, parentheses A intersect B intersect C equals A intersect B intersect C. To start this proof, use the tactic x. Notice that Lean has introduced the new object x u into the proof, and now your goal is now x is a member of A intersect B intersect C. Okay, so yeah, this is like that. If and only if x is an A. Okay, yeah. Okay, I see how this works. So it basically converted the equals into just an if and only if, but there's also an x. Proving this goal will show that A intersect B intersect C and A intersect B intersect C have exactly the same elements. And by the principle of extensionality, that will show that the sets are equal. Okay. So now what? I need to do the thing. Not you. Constructor? Yeah, constructor. Okay. So far, so good. And now I can do like intro H. I mean, that seems maybe good so far. Exact needs you to fill in the parameters, apply a smarter, and can infer. I see. So how do I do this? I think I need to use... Oh, do you think I need this guy to rewrite? It seems... I mean, it looks kind of like that, right? It does look like that. Okay, so we've rewritten one part of the goal. And then we rewrite the other part, sure. So we have a whole bunch of ands. Let me do the same to my h. Okay, there we go. So now everything is all splayed out. So I should just be able to reconstruct everything in one line. Okay, so what do we want first? We want the left part of h and then the left part of that. So h dot left dot left. Is that how that works? Am I cooked? Has object-oriented programming cooked my brain? Like, will it let me do that? Oh! Wait a minute. We're not done yet. Is that not allowed? Okay, maybe... maybe I cooked a little too hard. Okay, hold on. Let's go back. Let's go back. So we can have I don't know, let's call it L, which is the left side of H. Yes, good, okay. And now we should be able to construct part of this, I think. Okay, now we're good? Okay, now we're good. It is allowed. Oh, okay. Interesting. Yeah, I think it's because I accidentally left associated it instead of right. I think I had my parentheses wrong. But I think have just makes this a little bit easier to read anyway. So, whatever. I used a little bit of extra memory. Okay, so now you want me to do the same bloody thing I just did. But the other way, right? Okay, we'll just copy and paste. Yeah, that would be more like this case, I guess. But I don't know. I like doing the have. The have is just easier for me to read. just going to do h dot right so we can get this guy out. And then we can do an exact in dot intro with h dot, oops, no, with, okay, I guess I'm going to call this one r. With r dot right. And then sorry, what does it look like? Okay, so h, yeah, it'd be h dot left, and then h dot left. I mean r dot left. There we go. Okay, we're done. We can finally move on to Union World. Wow, it's time to unionize, guys. Okay, I think I actually probably have enough time for this one too, considering how that last one went. We'll see. I might only get through this partially. If A and B are sets, then the union of A and B, denoted A union B, is a set you get by throwing all the elements of A and B together into one set. In other words, for an object to be an element of A union B, it must be an element of either A or B, or both. For example, A is a set of all people under 30, not me, and B is a set of all people over 20. That's me. Then A union B is a set of all people. So even though there's some overlap, yeah, I guess that makes sense. In this world, you'll prove some basic properties of unions of sets. For working with unions, the important logical word is or. If P and Q are statements, then P or Q means P or Q or both. To enter the symbol or, type \or. For the statement P or Q to be true, either P or Q must be true. This gives us two ways to prove a statement of this form. If you have H colon P or then or dot in L H can be used to prove P or Q. If you have H colon Q, then or dot in R H proves P or Q. Okay. So what you're saying is I need to do exact or dot in LH. And now we're good. Okay, let's go. Mem union. So this is new. If you have X, U, A is set U, and B is a set U, then mem union XAB is a proof of the statement X is an element of A union B. If and only if X is an element of A or X is an element of B. In MATLAB, the name of this theorem is set.memunion. Okay. Yep. Makes sense. That's everything new. As with complements and intersections, one of the key tools for proving theorems about unions is a theorem stating the definition. If you have X colon U, A colon set U, and B colon set U, then mem union XAB is a proof of the statement X is an element of A union B, if and only if X is an element of A or X is an element of B. That means you can rewrite mem union to write out the definition of X element of A union B if it appears in any assumption or the goal. Okay. Similar to mem inter if. Gotcha. Why isn't this one called mem union if? I don't know. John Lean doesn't know? Does he know? He doesn't know. The naming of theorems in Lean is systematic, but there are occasional surprises. Huh. Not even John Lean knows why. What a mystery. So our goal looks like this. So we probably just need to... Wait, was it constructor or... Because I remember you can like double intro. Can I constructor here instead? No. No, I can just look at what constructor does. Oh, right. We need the if and only if for that. So I do have to do the double intro. At least I think I do. I thought there was like a shortcut you could do to avoid that. Maybe I am wrong. Writing out the definition of union and the goal should help you see how to proceed. Yeah, John Lean is not an all-knowing god. He isn't him. Okay, so H says A is an element of B. So I guess we just need to exact or.inRh. Okay. We'll see how to prove that a union is a subset of another set. Okie dokie. In this proof, we'll need a new proof technique, proof by cases. And we'll need a new tactic to implement that technique in Lean, R cases. Okay. Of course, to start a subset proof, you need to introduce an object X and an assumption H3. Sure. Wait. Introduce an object X and an assumption H3? Are you saying I should intro X? Oops, I'm pressing the wrong buttons. I think I pressed like the Alt key. Like this? I guess they don't like me using the letter A because they're using it for like the elements of like A or B. Or actually, I think they just like the letter X. They've been using X a lot. That's probably why they want me to go intro X. To understand the logic of this proof, it'll help to write out the definition of union in H3. Wait, didn't we already do cases before? I swear we did a cases thing. But it wasn't called R cases. I think it was just called cases, right? Yeah, I remember this. R cases. If H is a proof of a statement of the form P or Q, then the tactic R cases H with H1 pipe H2 will break your proof into cases. In case 1, you'll have the new assumption H1 colon P. And in case 2, you'll have H2 colon Q. In both cases, you have to prove the original goal. The R cases tactic has other uses. In particular, it can be applied to proofs of statements that do not have the form P or Q. However, we will not discuss these other uses of the R cases tactic in this game. Okay. Write out the definition of union in H3. Okie dokie. So you want me to rewrite using mem union? Mem union. At H3. Now the assumption H3 is an OR. The easiest way to use such an assumption is to break your proof into cases. To do this in Lean, use the tactic R cases H3 with H3A bar H3B. Now you have two goals. For the first, the assumption X is an element of A or X is an element of B has been replaced with X as an element of A. And if a second has been replaced with X as an element of B, in both cases you need to prove X is an element of C. The two identifiers after with in the R cases tactic are used as the identifiers of the new assumptions in the two cases. Okie dokie. We did cases in NNG, though it seems there are several variations of the cases tactic with various syntax. Really? And they're all part of Lean? Why don't they just have one? Like, why can't we just have cases? Why do we have R cases as well? Who would do such a thing? I mean, there has to be a good reason for that, right? I can already see left and right are here. Oh, and there's also a by cases, apparently. Okay, so I need to apply H3A to H1. Okay, and that should give me back what I want. So exact H3A, H1, H3A. And then we do the exact same thing here. Exact H2, H3B. There we go, easy. Note that Lean also has a cases tactic, but the syntax is a little more complicated. That's why we have chosen to use the R cases tactic. Oh, they tell you right here. The R cases tactic has other uses. However, in this game, we will be using it only with assumptions that are OR statements to break the proof into cases. I see. So John Lean explains. John Lean tells all. In the next level, we're going to prove that union is commutative. That is, A union B equals B union A. We're going to imitate the approach we use in intersection world to prove that intersection is commutative. We begin by proving A union B is a subset of B union A. Uh-oh, I have to recall what I did in intersection world, but that was like a forever ago. Okay, so I think I need to intro. Yes, intro X. And then we got to intro again. Okay, now they're giving me hints. It's not quite hint time yet. We're gonna have to break down the definition. So I'm gonna use mem union. And we're gonna use mem union again. But this time on H. Now we have some ORs. How exciting. So I think we need to R cases H with H1, H2. I guess they would probably want me to call it HA and HB. I'm gonna try and stick with a naming scheme that they would like. I don't know why I'm being so picky about this. Exact or dot in R. Aha. And then exact or dot in L. Hub. Okay, cool. You'll be able to use the theorem union subset swap in the next level to prove that union is commutative. And that's what we just learned, right? A union B is a subset of B union A. Makes sense. If you start your proof with apply subset.antisim, then you'll be able to use the theorem union subset swap that you proved in the last level. Will do. Why make things harder? Aha, okay. So I can just use this boy exactly. Although I guess I could just apply it, right? And now we have a new goal. B union A, the subset of A union B. And this one's going to be the same thing. Okay, cool. Next, we'll prove the associative law for unions. Oh, look at all these text things. Here's an idea that you may find helpful for this proof. If you're proving an or statement, and you think you'll be able to prove either the left or right side of the statement, then apply or.inl or apply or.inr will set the goal to be the left or right side. Okay. Alternatively, the tactic left has the same effect as apply or.inl, and right has the same effect as apply or.inr. Ah. So that's how they tie left and right back in with this stuff. Okay, I see. You can start this proof with either x or apply subset.antisim. We did x last time, so I think I'm going to do it again here, just to try and keep it in line with what we did last time. Notice that, as with intersections, lean groups unions to the left. So A union B union C means A union B union C. And we get our good old friends left and right. Gotcha. And here's our union com. Right, A union B equals B union A. And if we use x, if our goal is an equality, then it gives us an if and only if. Boy. And if we have an if and only if, then we need to use the power of... this is one where we use constructor, right? E. Constructor. Intro H. Okay, and now we need to break down these guys with rewrites. So that is using mem union. Yes. We'll do it again. And then we're going to do it again. But this time at H. And we're going to do it again. All right. Everything's all splayed out. Now I can prove any of these things. Except, how's that going to work? Because, like, I could... So they want me to left or right here. I guess if I do a right... I could do another right. So now my goal is to prove X is an element of C. But can I actually prove that? Because X is an element of A, or X is an element of B, or X is an element of C. So how would that work? Do I need to R cases first, maybe? R cases H with HAB, HC? That seems like the right way to go about this. Yeah? And then we need to R cases U. Okay, there we go. That's looking good. Because now I can left and then exact HA. There we go. Okay, now I'm getting the hang of this. So if I right, then I can go left. And now I can exact HB. And it feels like it wasn't even that long ago when I was struggling with this left to right in cases stuff. Now it feels so easy. But maybe it's because R cases is easier to work with than regular cases. Okay, now we need to do another intro. H. Oh, this is a long ass proof. Okay, and then we're gonna do our block of rewrites again. I'm sure you could make this shorter, but it's fine. Okay, so you're at the top level. Okay. Now we just need to go left and then left again. Exact HA. Then we need to R cases HBC with HB. Oops, HB, HC. And then we go left, and then we gotta go right. And then we go exact HB. Then we go right. And then we go exact HC. Okay, very mechanical. You've mastered reasoning about complements, intersections, and unions. In the next one, we'll start mixing them up. All right, cool. And I think that's all the time I have for today. I guess we could start on the next one. We actually have 2 worlds to choose from. I'll start with the smaller looking one. We'll look at this guy, combination world. In this world, you'll prove theorems combining complements, intersections, and unions. For the most part, we'll leave you to figure out. We'll leave you on your own to figure out these proofs. Ooh, okay. All right, so here's where things get difficult, I guess. There's more than one way to do the proof in this level. Since the proof involves complements of sets, negative statements will arise in the course of the proof. This suggests 2 possible techniques. You may be able to use the push neg tactic to re-express some negative statements as equivalent positive statements. And you may find proof by contradiction useful. I see. All right, so the first thing I'm seeing is an equality, which makes me feel like I should use either X or anti-sim. Actually, where is anti-sim? I mean, these are kind of similar. I don't know. I'm just gonna go X. X. And then we're gonna use a little bit of constructor. Okay, so what do I need to do here? Intro, I guess. Okay, so now we have U. I'm gonna rewrite. Where is mem inter if? All right, cool. I'm gonna rewrite. Oh, wait, I can't rewrite this yet, can I? Because of you. You're here. So what can I do about you? I don't know if this is helpful. Okay, I think we want you. Okay, so now we have our union. I need to do something with you. By contra? Okay, I think we might need to... Well, this is not my goal, though. Oh, but I could do it on these guys, too, couldn't I? Okay, okay, okay. Yes. Okay, so somehow I have to prove both of these. But I also have you. Is there a way I can get, like, the left side of this only? Like, so I can, like, break this down and prove each of them one at a time? Let's see. Okay, I can do this. And that'll let me prove each of these one at a time. Sure. So now from here I can do something with you, right? Because you're like a knot. So I can prove this one by contradiction. What can I do with you? So I need to process this guy. Push neg, push neg, push neg, push neg. Oh no, push neg doesn't work here. Okay, but you are negative. Oh, constructor would have worked there? Okay. Yeah, that puts me in the same place. Oh no, it's the wrong one. Shoot. Oh wait, can I rewrite? I can do that. Oh, okay. So it does let me do this. Even though it's under the knot. Can I do an intro at? No. How do I convert this into a thing I can work with? Because I don't think I can R cases this with this knot in front of it, right? No. That's what I thought. So I'm not allowed to do that. Oh, wait, hey, hang on. Push neg. Now I push neg. There we go. Okay, okay, okay. Now things are starting to add up. And then I can do... Right? Wait, and then I need to rewrite this guy. Wait, why is it not like that? Oh, H1. There we go. Now we do this again. So we didn't even use R cases here. But it only works because we're using push neg. Okay, and I can't push neg yet until I rewrite. Okay. And then we can push neg at h. Now we can do exact h no right, h. Wait. I forgot to buy contra. Actually, do I even need to buy contra? Oh, I've overcomplicated this. Okay, well, it doesn't really matter. Okay, well, I feel silly. Okay, so now for you. Intro H, I guess. Okay, seems good to me. We'll rewrite mem union. Oh, I can't do that because of the C, right? Okay. So don't do that. What about mem compile if? Yeah, you like that. And then I can do a rewrite mem union. There we go. Ooh, what if I push neg? Interesting. So I could do this. Get an and out of that. I'm going to try to rewrite mem compile if at h. And I'm going to do it twice. Okay. Hey, we can just do exact h and win. Yo, let's go. Level complete. All right, cool. Well, that is all the time I have for today. So thank you very much for watching my struggles, trying to reacquaint myself with Lean, relearning stuff, just learning new stuff too, of course. But yeah, this is cool. This has been going pretty smoothly. This is definitely feeling easier than natural number game so far. Like law stuff just flows super nicely, and you don't have to like do like crazy induction or anything like that. I think the lack of induction is honestly making this a lot easier. I think that could have been much shorter. Really interesting. I wonder how. I mean, like, it worked. Maybe if I didn't do X, maybe if I started with like anti-sim instead. But I don't know. It's fine. I did it. I completed the level. So yeah, there's a little sneak preview of what we're gonna do for next time. But yeah, this is our progress for today. We're about we look like we're maybe halfway through. We did the first 4 worlds, dipped our toes into combination world, and then we have 4 more worlds left to go. I suspect that things will start to slow down as things get a little bit more difficult, especially here, I imagine. So this might take another extra week to finish. We will see. But that's going to do it for today. Once again, thanks for watching. And I will see y'all on Tuesday with more Gen 2 Rescue.